Okay. And before we come to the vote, I would like to put up this here. This is the exercise we have been discussing yesterday in my study group. And since I got a few questions of students after the study group which could not join because they were also interested in another group about this, what we did, I put it up here. So this is the exercise. I will leave it there for the rest of the lecture. So you can copy it, and if you like, you can try to work it out and discuss with me. And for the study group tomorrow, I suggested on the list that we will discuss, inspired by Moise's comment, that we will discuss thermal ratchets a little bit. But if you rather prefer to go through this exercise, this is also fine with me. So it's what you prefer to do, what we're going to discuss during the working group. And of course, there are plenty of opportunities to approach me during coffee break, between the talks, during poster session, whatever, and we can discuss questions, and I can explain things if you want to know more. Okay, right. And now to the vote. Who wants? I have two piles here, two piles of notes. And it depends on you now which one I'm going to use. So charge effects, electric double layer, hands up. Okay, this is roughly like 10-ish. Stochastic thermodynamics, hands up. Okay. It's a little bit more, not so many. I don't care, hands up. Okay, let me repeat. Stochastic thermodynamics. And charge effects. Yeah, okay, it's stochastic thermodynamics. It's a close call, but it's stochastic thermodynamics. That's this pile here. Okay, you have seen already quite a bit yesterday in my talk, and what I'm planning to do here is to go into a little bit more detail. So this will still be a very small selection of results which are known in the area. I mean, it's just the very, very basic. It's an extremely active area, and if you Google it or so, you find certainly about 10 review papers written in the last few years on experiments, on theory, and you will find developments in quantum theory, quantum thermodynamics. You will find things about information. You will find things about adaptation, evolution, and so on and so forth. So I'm sticking to the very, very basic, and I'm also focusing just on the Langevin equation and on the classical Langevin equation. And what I'm going to present here goes basically back to Sekimoto. I leave it there for you, the exercise first. So this was one of the references yesterday in my talk, the book by Sekimoto, Ken Sekimoto, about stochastic energetics, one of the inventor of this whole area. And then it goes also back to the work of a German guy, Udo Seifert, who actually introduced this concept of defining entropy production along trajectories. So this is the main thing I'm going to talk about. And so let's start here. Stochastic thermodynamics. As said, the system stays the same. It's our particle, yes, thank you, in aqueous solution, this colloidal particle, micrometer, let's say, performing Brownian motion. And we have discussed stochastic dynamics already. And now the question is, can we do stochastic energetics? or stochastic thermodynamics. And following the inventors of this field, Sekimoto, he's in Paris. He says stochastic energetics is the missing link between stochastic dynamics, that is what we discussed already, and thermodynamics. So what he means is the following. If you have this here, this box represents stochastic dynamics, and this one here is micromechanics. So this is actually writing down the Newton equations for all particles involved, including all the particles of the solution and everything you have. Then you get from here to here by, for instance, projection techniques. So we didn't discuss these in detail, but I mentioned that there are ways to sort of derive from all the equations of motion by applying certain techniques to derive stochastic dynamics. And this is this step here. And then on the other side here we have thermodynamics. And the link from micromechanics to thermodynamics is statistical mechanics. So this here, this whole sketch is from Sekimoto's book, from his introduction. And what about the link here? Okay, there is no real link that we know. And Sekimoto says stochastic energetics is this link going from here to here. And then you add as a connection as well, and this is then what SAIFR says. Udo Seifert, he's in Stuttgart. He says stochastic thermodynamic combines the stochastic energetics with the idea that entropy can consistently be assigned to single trajectories. I write it shorter with entropy production defined along fluctuating trajectories. After all this has been developed a little bit, people are saying more now that this whole framework should be called trajectory-wise thermodynamics, because you define the thermodynamic concepts on the trajectory level. And much of this development on the theory side, so this here is stochastic thermodynamics. Much of the development on the theory side here has actually been driven by also the development on the experimental side, that you could do better and better experiments and resolve more and more details what is going on in biological system, what is going on in the cell, and so on and so forth. And it was clear that these systems are like yeah, it was mentioned already several times during that school that a cell is like a huge machine converting energy, performing tasks. So there is a natural way to think of these things in thermodynamic concepts. And this has been driving the development a little bit, and also that these systems are out of equilibrium. These are all out of equilibrium system. So it's a big difference to classical thermodynamics, which concerns only equilibrium systems. This is one of the characteristic features of the systems here, that they are driven out of equilibrium by external forces. So we have discussed optical tweezers, for instance, a potential, let's say a parabolic potential, trapping that particle, and then you can move it around. Or in the cell there is energy conversion going on all the time. There are chemical gradients and things like that. Another characteristics of these kinds of concepts here is that the objects you are interested in, the system, are embedded in a thermal bath. In that case, it's the solution, okay, which is responsible for the thermal fluctuations. So there is something which provides a temperature, for instance, or a pressure, and so on, because for just one single particle, these concepts are often not well defined, in particular if this particle, this object, is driven far away from equilibrium. This bath somehow gives us the connection to standard thermodynamics. And we have seen already yesterday in the talk that then often the results are refinements of inequalities we already know, like the second law. The second law is then replaced by a better equation, which is an equality. And then by the properties of the functions involved, you recover the second law. This is what I've already discussed yesterday a little bit, and we will go more into detail right now. So in the end, you see, by these results I've shown already yesterday, that even non-equilibrium systems of this kind here obey a surprising symmetries. You can say quite a lot about these systems, even though they are driven out of equilibrium and are subject to thermal fluctuations. This has been, I think, quite a surprise to many people when these equations have been discovered, that you can make quite strong claims about those systems. So also quite generally valid, like the fluctuation theorems and consequences derived from that. Okay. So our model class is the Lorentz equation, gamma x dot of t equals, and I write it now, I write the force in terms of a potential, du dx of x of t, and then there is the thermal noise, 2 kpt gamma psi of t, and then this potential here can be explicitly time dependent. I would like to have the possibility to manipulate my system that I am studying. And this here in that lecture, this is represented by some control parameter lambda of t. This parameter represents the protocol an experimentalist applies to that system, moving it around, like in this experiment, folding and unfolding an RNA hairpin, or things like that. So this is represented here by an explicit dependence on time of the potential, or on a control parameter, lambda of t. And a thing that is very often a little bit confusing in this setup when people discuss these things is the separation between what is my system, what is the rest of the world, what is an external agent. And for that reason, it's quite in detail discussed in Sekimoto's book. And I also would like to make it more explicit so that the system we are always interested in is a part of the whole world we are interested in. And its state is represented by x, by the state variable x. And in our case, it's modeled by a Lorentz equation. So we have, for this state, we have an equation of motion, typically a stochastic equation of motion. And the potential energy, which I write down here, is part of the system. This is the internal energy of the system. And then I have a thermal environment which is characterized by a temperature T. This is the bath the particle is suspended in. And everything what my system does has no effect on the thermal bath. Okay, the thermal bath is so huge and so fast that whatever my system does not change any of the properties of the thermal bath. That's an important ingredient. So in a way, it returns instantaneously to its equilibrium state once the particle moves. And this is justified by this huge separation of time scales that I mentioned already several times. It's a very important ingredient. The assumption that this is always in equilibrium. At this temperature here. And it's also not affected, the bath is also not affected by what is called the external agent. And this external agent is the parameter lambda of T. And this external agent, he or she can manipulate the system in some way, can macroscopically control the system. It's basically the experimentalist, if you think about these typical optical tweezers experiments. And by varying lambda, work is performed on the system. This is the way you perform work, or the system can give back work to the machinery that is built to control the system. So this thing here is connected to the work. I'm going to describe in more detail in a second. An important thing is also that the time evolution of lambda is not part of my equations of motion. It's really something external. I have the system has no control over. So time evolution is not part of the equations of motion. And this subdivision depends on the question you ask. And the most important thing is to identify your system. If it's just one particle, in a huge bath of other particles in your cell. You're focusing on one. Maybe it's several. Maybe it's a whole collection of certain proteins and things like that. So what is system or thermal environment can depend on the question you are asking. But it's important to have this separation in mind to understand better what happens. And I have the impression that one source of the confusion when you talk to people who know thermodynamics and statistical physics is very often that when you say system, they think about a gas, a container filled with gas, for instance, or with the water. So they think the system is actually the water here, because this is my part which is in thermal equilibrium, which is actually described by thermodynamics. But in this setup here, this is not the system I'm interested in. I am interested in what is going on with a particle when I manipulate it. And in that respect, the bath is only the thermal environment, but it plays an important role, of course. Right. So and as it turned out in this whole development of the theory, when you do thermodynamics, you consider the state of the system. It does not change over time in equilibrium. That's the very definition of equilibrium. It's the state of the system. You can do manipulations by removing constraints. I discussed that a little bit. Then you wait until the system is in equilibrium again, and so on. So in that sense, you just go from one equilibrium state to the other equilibrium state without really knowing what happens in between. Here, you follow the whole trajectory and do thermodynamics on the trajectory level. And this realization that you have to include the whole history of the system to extend the concepts of thermodynamics to these non-equilibrium situations led to a paradigm of experiments, or also of a way to think about these kind of problems, which is the following paradigm of a non-equilibrium process. First, the system is at equilibrium. You start from an equilibrium system situation. So it's in equilibrium with a thermal bath for some value of lambda, which I call capital A. You start from a situation, you prepare your system and let it equilibrate. Okay? And lambda has a certain value, which is A. Then, from the starting time point, which I set to 0, to a final point, the system is perturbed by varying lambda. My external control parameter. So I do something. I pull the RNA string, I move the colloidal bead in optical tweezers, or things like that, until I reach a value lambda equals B. So I go from A to B by doing something. And this protocol has to be defined in some way. And it can lead the system very far from equilibrium, because you can disturb a lot. Okay? When you're doing something and you're doing it violently enough, let's say you don't allow the system to equilibrate with the thermal bath during that perturbation. And then, after that, lambda after the time point, the parameter is held fixed so that the system can equilibrate again. Okay? So you start from an equilibrium situation, you do something, you're done with doing your manipulation, with you doing your experiment actually, and you stop and you can wait so that the system equilibrates again. So you're starting in an equilibrium state and you're ending in an equilibrium state. And in between, something happened and the system had been driven out of equilibrium. And then repeating this experiment many times with exactly the same protocol lambda of t, this is important. And repeating this experiment many times, what you get is a distribution of the relevant quantities. Because of the thermal fluctuations, in every realization, even though you start from the same state and end in the same state, but because of the fluctuations, what happens in between is every time it's different. So any quantity you measure will give you a different value, or almost any quantity. Okay, so doing this experiment many, many times leads to a distribution of the quantity you're interested in. For instance, let's say the work. So distribution let's say of the work performed during the variation of lambda of t. And of all the other quantities too, of course. And then we know from classical thermodynamics, which should be valid, that the average work should be larger or equal than delta F, the difference in free energies. So this is the free energy at the final state B minus the free energy of the initial state A. So the change in free energy going from this equilibrium state to this equilibrium state. And the work here should be larger than delta F, or at least equal if you do it adiabatically. And this is a formulation of the second law. This is the Clausius inequality. This is standard thermodynamics. And it's exactly what I said before. This equality here, inequality, does not know anything about what happened in between. It only knows about A and B, where the thermodynamic concepts are well defined because it's equilibrium situations. Now these concepts here, they take into account the information that is contained in the variation here by having access to the equation of motion. Okay, and when you get this, when you do this, what you find then is the Shashinsky relation, which I already presented yesterday, which is the average of E to minus work divided by kBt is equal to E to minus delta F divided by kBt. Okay, now this average here is over all the possible realizations, all the possible experiments, and you do this average, which is a non-equilibrium work here from the non-equilibrium process, and you get the information on the equilibrium free energy difference, and this is an equal sign. So it's a refinement of this here. And this equation actually follows from this one by Jensen's inequality. Because the exponential function is a concave or convex function, whatever. And then you can prove that the average of an exponential is larger or equal than the exponential of the average. Okay, so you get this from that equation here. Right, so this you have seen already yesterday. And this is in more detail explained the central idea how you extend stochastic thermodynamics, or how you extend thermodynamics to stochastic systems by taking into account what happens here along the trajectories. And how you do that, I would like to describe now a little bit more detail, starting again with stochastic energetics. So first, the question, what is heat? So I said already yesterday, heat is energy exchanged with a heat bath, per definition. And the energy exchanged with a heat bath over a displacement is the force exchanged with a heat bath, which is friction and fluctuations at a certain time point times the displacement dx at this time point. Okay? So this here is the heat exchanged with the heat bath over a displacement dx when these forces are acting. Does that make sense, this definition? I mean, in the beginning of the field, this has been really, people have discussed it a lot because it's force times displacement, and you would say this is work. Why do you say it's heat? It's correct, it's work, but it's the work exchanged with a heat bath. So this is exactly what heat is in the end, or heat exchange, I should say, right? So if you change the energy content of the heat bath, then this is the heat exchanged with the bath. Okay, and now if we look at the energy change of the potential, we get the change from the position of the particle, du dx times dxt, plus the change due to the variation of the control parameter lambda, d lambda. Okay? So we get two contributions from the change of the internal energy of the system. And from the equation of motion, we see here, if you bring that to the other side, that this part here is given by minus gamma x dot of t plus square 2 kpt gamma psi of t dx. So this is actually the heat, just by the balance of the forces. Okay? And then we have this thing here, which we have to identify then as the work. And this here is the heat along this step. So from that, we get the first law that du x of t lambda of t is equal to delta q, the heat, plus the work, where the work is defined as du d lambda times d lambda. This is the work done by the external agent on the system. And of course, I can integrate it also over the whole trajectory. Integrated along trajectory. So this gives then the work of the whole trajectory as the integral from the time where I start to the end time, du d lambda, or I can write here lambda dot dt for the d lambda. And the heat of the trajectory is given as the integral 0 to t du dx x dot dt or dx, whatever. Okay, and then I have a first law on the trajectory level. And this here, this work, is actually the object which enters here. Yes. Sorry, can you repeat? This here? Yes, from the equation of motion, from the force balance. So you bring that over here and that here, you get d or dx. Okay? It's the force balance. You can also do the same thing for the Longchamp equation, including inertia effects. Then you have a contribution from the kinetic energy as well. Sorry? The kinetic energy, or what? Here, yeah, right, sorry, yes. Thank you. Yes? Yes, this is the external work. This the du d lambda d lambda. Okay? Or lambda dot dt, like I wrote here, when you integrate. Okay? So this is the work performed on the system by the external agent. By the way, I'm doing here the calculations using usual rules of calculus. For the experts, one has to be a little bit more careful. There's the Ito-Statonovich thing because of the weird properties of the white noise. Just so that you know, I'm a little bit sloppy here. I'm not mentioning that. These here are actually all Statonovich products, for those who know what that means. If not, you don't have to think about it now. Okay, and and when do I have to stop? Huh? Okay. So now this is first law, the energetics. What we now need is entropy. And so this is a suggestion by Seifert. The heat dissipated into the environment should correspond or corresponds to a change of entropy in that environment. So the change of entropy in the medium, I add the index m here for the medium, along this trajectory is then equal to minus q of x of t divided by t. So this is just usual thermodynamics. And why can I do that? I can do that because the environment is a system in thermal equilibrium all the time. So that's also the reason that there is an equal sign and not, the entropy is usually larger equal Q divided by T for arbitrary processes. But from the perspective of the bath, it's an equal sign because the bath is in equilibrium all the time, no matter what our system is really doing. Okay, so this is the entropy production in the medium. And then this is entropy production in the medium. The bath. And the contribution of Seifert is to suggest definition of an entropy of the system, which is given by that. Entropy of the system along the trajectory. Where this P here is the solution of the Fokker-Planck equation. corresponding to the Langevin equation of motion. Okay, so this is the entropy of the system along that trajectory x of t. You plug in x of t here. And since you're manipulating the system externally by varying the parameter lambda, also the probability distribution may directly depend on time, not only on x. Okay, why does it make sense to use such a definition? Why is it useful? First, when averaging this here, this definition, S of t, this is this here. Now I do a small calculation. Using the definition of the probability distribution, I first introduce an integral dx with a delta function, like that. Okay? So, in principle, I have nothing changed from here to here. The only thing is I write this integral here, and this says, okay, whenever x is equal x of t, you have to pick x of t. So I can write here x of t or x, whatever I prefer in principle. So again, x of t and x are different mathematical objects here. But now, I can take this average into the delta function because it's an average over the trajectory. So I get minus k integral dx delta x minus xt averaged ln p of xt. But this here is actually p of x itself. It's the definition. So meaning that I get minus k dx p of x of t ln, so this is kbt, this is kb. P of x. So I get the standard ensemble average of the entropy here by averaging. So this is one motivation. That's motivation number one. Motivation number two is that in equilibrium, so when the system is equilibrated with a bath, then P of x and t is equal to, so that means that lambda is some constant value. It's given by 1 over c e to minus u of x lambda divided by kbt, which is equal to exponent of minus 1 over kbt, u of x lambda minus f of lambda, the free energy, where the free energy is defined as usual minus kbt logarithm of the partition function, which is minus kbt logarithm, I have to write the next line, logarithm integral dx e to minus u of x lambda kbt. So this is standard definition of entropy. And when using this here, taking the logarithm minus kb, we get that the entropy S of t along the trajectory in equilibrium fulfills the standard thermodynamic relation that it is equal to u internal energy minus free energy divided by t at any time point along the trajectory. Okay? So this is also something which makes absolute sense, that in equilibrium, you should have the equilibrium relation at any point in time. Otherwise, the concept you define does not make sense. And the third motivation is that the total entropy change along a trajectory, delta S total, which is defined as the sum of the change in the medium plus the entropy change in the system, where this delta S here is then the integral of the entropy change along the trajectory, and it's equal to minus KB ln P at the end point x tau plus KB ln P at the initial point, which I abbreviate with some initial distribution. Okay? So this is the change in entropy. If you like, it's along this trajectory by integrating the rate of entropy change along the trajectory. And this thing fulfills, the total entropy production fulfills an integral fluctuation theorem. Which you have also seen before, e to minus delta S tot divided by KB averaged over all realizations, over all possible experiments is equal to 1. So, and from that, again, by Jensen's inequality, we get that the total entropy change is non-negative always. So this is, again, a refinement of the second law, if you like, because it's not just an inequality, but an inequality for a slightly different quantity. You repeat this experiment many, many times, average the entropy production, the total one you got from the experiments, and you find this. And from that, you get the second law. And this makes sense. This is now the total entropy. So it's the entropy of the system and the bath. So everywhere where we change the entropy by doing this experiment, if we take everything together, this fulfills the second law. Okay, and now this almost looks as if we now were able to derive the second law from the underlying dynamics, from the Langevin equation, and this we actually do. We can derive it now from the Langevin equation, but since the Langevin equation already breaks the balance, or it has a friction term and fluctuation term, I have built this in from the very beginning in a way. So it's not a derivation of the second law from fundamental principles. This is not what happens here. Okay, now I have been a little bit slower than I thought. The last part of the lecture I had been planning to prove this fluctuation theorem. It's a small calculation, but I think it would probably take 15 minutes. So does my co-organizer grant me this extra 15 minutes and the audience? Okay, good. Then I will clean the blackboard first. Okay, the fluctuation theorems. We prove the fluctuation theorems by first proving a slightly different relation. We will prove that e to minus delta s m divided by kb times p1 of x tau divided by p0 of x0 averaged is equal to 1. This is what we are going to prove. And then we will use that to prove the other relations. I will show how that works. And P1 and P0 are arbitrary normalized functions. So probability densities, if you like. P1, x tau, and P0 of x0. Two different probability densities. They are normalized, depend on this one depends on the initial position of the particle of the system, and x tau is the final one. Okay? And for now, they can be arbitrary. Okay, and first we start by deriving an expression for the change of the entropy in the medium along a certain trajectories. And we do that by using path integrals. So the first step is derive expression for e to delta Sm divided by kb. From the Langevin equation, x dot of t, I write now here v of x of t, lambda of t, plus square root 2d psi of t. And this v here is minus du dx x of t, lambda of t, 1 over gamma. It's just an abbreviation. So the first step here is that we write down the transition probability, P of x at a time point t plus dt, given that the system was at a position xt t at an earlier time point. Okay, so the idea is that we have a certain path starting here, particle is moving, ending here, and we subdivide this path in small parts of length delta t in time. So we sort of discretize it. And for all these small steps, we have a transition probability going from the first position to the next one. So here, somewhere here, we have xt, and then the next step would be xt plus delta t. But this here, we already calculated, or I've written down, right? So this is equal to 1 over square root 2d delta t e to minus xt plus delta t minus xt squared divided by 4d delta t. And here this is actually 4 pi d. And then we have minus Vt delta t here. So this is now in the notation we use here, the same expression we had yesterday. Okay? And then what we want is, we want to have the probability for a certain path, x of t, given we start at an initial position x naught. And we divide this path using the Markov property into a step that I'm x delta t at delta t when I started at x0, 0. Should write start from here. So this would be my first jump. I start at x0, at time 0, and I jump to some position x delta t after a time delta t. My next jump is that I start from x delta t at delta t, and I jump to x 2 delta t after 2 delta t. Okay, so I subdivide the trajectory in all these little jumps until I end up at x tau at the end point here after time tau, and before I was at a position tau minus delta t at the time tau minus delta t. And you see all these transition probabilities are Gaussians, product of Gaussians, which give a sum in the exponent. And then I take the limit of delta t going to 0, so infinitely many steps, and all these sums here in the exponent go to an integral. So this here goes to the exponent of minus 1 over 4d integral 0 to tau of x dot of t minus v of x of t lambda of t squared. Okay? So all these exponentials, products of exponential, in the exponent is a sum over all these points, and then I make this the discretization arbitrarily small, and I end up with the usual integral. Okay, 2 comments here. First, there is a prefactor, a normalization, which is actually infinite when I do the limit, but it's not dependent on the specific path. Okay? So I know the path probability up to a proportionality factor, which is not important, because in the end I will take ratios of path probabilities. Second comment, I've been sloppy here, because the discretization, I should in effect be a little bit more careful. This is again related to the Ito-Statonovich thing, and if you are interested, you can ask me. But for what we are doing here, this is fine. So this is not mathematically exactly precise what I'm doing here, but it's good enough. Just side comment. Okay, so we found actually the path probability. I'll write it here. This is P of x of t given I start at a position. It's proportional to this exponential. Okay, and now for the next step, we have to look at the time reverse trajectory. So this is the probability of observing a path, and we are going to compare that with the probability of observing the path backward in time, traced out backward in time. This is a very central concept here, also in stochastic thermodynamics, that we compare forward and backward processes, time reversed path, and also protocol. So I have to inverse the protocol too. So I look at a path which I label by a tilde, and it's defined by the forward path backward in time. So you see, if time is equal to 0, I start at the final point, and when time progresses forward towards tau, to the end point in time, I end up at x of 0. So it's exactly the trajectory traced out, and I do the same thing with the protocol. And now since I want to compare these probabilities, for the forward and backward path, I will try to express the path probability for the backward path in terms of the forward path by using this relation. Otherwise, I cannot compare them. So this here will be, I just plug in the tilde expressions, minus 1 over 4d, integral 0 to tau, x tilde dot of t minus v of x tilde of t, lambda tilde of t squared. Yeah, so dt. Probably forgot a dt here too, dt. Okay, and now I use this relation, plug this in. Now first I change the time variable. I introduce t tilde equal to tau minus t. So that I get the integral here, minus 1 over 4d, integral still from 0 to tau. This gives a minus from the integration variable dt here. dt tilde is minus dt, and this minus I use to switch the integration limits. And this will then be x tilde dot of tau minus t tilde minus v of x tilde of tau minus t tilde, lambda, the same, squared dt tilde here. Okay, and now I can use these relations here to replace the tildes by the original variables. And at the same time, I have to take into the consideration that the dot here is the derivative with respect to the t, so that I get a minus here from the time derivative, minus x dot of t minus v of x of t lambda of t squared and dt. So I also replaced, so this here, this x tilde of t minus t tilde is x of t tilde, and then I just use t again. Forget about the tilde. Okay, you see it's the same path probability, the same expression, except for this minus here. So the backward path is almost the same. And the difference is actually this here, this square, is actually x dot minus v squared plus 4x dot times v. Okay, without the arguments. So if we take the ratio of these two probabilities, what remains is just this term here with a 4. So it's exponential of minus 1 over d integral 0 to tau x dot of t v of x of t and lambda of t dt. Okay, and this here is actually the heat exchanged along the trajectory. So what I find here in the end is that this is the exponent of, since it's divided by t, it's the exponent of delta Sm divided by Kb. So this is how the heat is connected with the entropy production in the bath, which is connected to the irreversibility of single trajectories. So the entropy produced in the medium, in the bath, along a certain trajectory tells me how irreversible this trajectory is, how likely it is to observe it backward in time. Okay, so now this is a detailed fluctuation theorem. This is how it's called. And for the full normalization along a path, if we write down the path integral, so we integrate over all possible paths, this probability density, we have to multiply also with an initial distribution, which is normalized to get the full normalization. So this is this normalization condition along a full path, and it's the same for the backward path here. 1 is equal to the path integral of the backward path for the backward path probability, which starts at the end point of the trajectory, and then I can use here again any arbitrary distribution to get the normalization. But this I can rewrite now using this thing here, again in terms of the forward path. So what we do is we write down this path integral and introduce the forward path probability. In that way, so I just do it like that. Okay, nothing really happened. I just introduced this term here. But this ratio I know from this calculation here. It's minus delta Sm divided by Kb. And then I have the P1 of x tilde naught. So it's the final point of the trajectory, which is also the same as x tau. And here I have the initial point. And here I have the full path probability with a normalized thing. Okay, and then I can actually skip the tilde symbol here in the integration measure because the set of path is the same, no matter if I look at them forward in time or backward in time. So the integration measure is the same. So I have 1 is equal to this integral. So this here is actually the quantity I wrote down here. And this integral over all possible paths is what these angular brackets here represent. So we found this relation, okay, from this calculation, from doing the path integral. Sorry? Which equation? No, there is no change in the integration limit. So, okay, let me do it like that. That may be more clear. I did not change the integration variable. I just changed the symbol, but this is confusing. So it's still the t tilde here, which is the same as here. Okay, I just used these relations with a different symbol for the t. Okay, just a different symbol in that case. Right. Oh, that was a little more than 50 minutes. Oh, we are almost there. Yes. Okay, now we use this salt here. I need a little bit more space. We first prove Straczynski relation from that. So remember, these two distributions are arbitrary. I can plug in here whatever I like. So this is a very general relation. And in the end, it's related, that this is so general, is in the end related to the fact that I have defined it using a ratio of probabilities. Okay? And the ratio of probabilities, if I bring the other probability to the other side, I can always normalize it. The thing here is, the central thing is that we can interpret this ratio of probabilities in physical terms, namely by identifying it with the entropy production in the medium. That's the important thing here from a physics viewpoint. So now we can do here whatever we like, and we choose here for P0 the equilibrium distribution at initial time with some initial value of the parameter lambda. And this is then the same as I wrote that down before, writing it with the free energy, which comes from the partition function here, which is basically the logarithm of the C naught. And we can do the same thing for the final distribution using the final point and the final free energy. And then we use that delta Sm divided by kBt is equal to plus q along the trajectory divided by kBt. No, there's no t here. Just like that. And this is equal to 1 over kT, the heat, by the first law, the energy change delta U minus the work. Okay? And the energy change here is actually the difference of these two values of the potential. So, and if we plug these two distributions in, use this relation, then we actually find that e to 1 over kBt delta u minus w, and then this comes from this part here. This is the entropy. Yeah, I should write it more clearly here. So we get e to 1 over kBt delta u minus w. This is the entropy change in the medium, and then comes the contribution from these two distributions, which involves quite a number of terms. 1 over kBt times u of x 0 lambda 0 plus u of x. So this is tau here. 0 lambda 0 plus f of lambda t minus f of lambda 0 is equal to 1. Okay, and then you see that all the terms which are related to the internal energy of the system drop out, and we indeed are left with Jarzynski relations. Where delta F is the free energy difference. Okay, this is this relation here. It's a derivation different from Jarzynski's original derivation. He derived it for Hamiltonian systems. But here we derived it for Langevin dynamics. So as I said also yesterday, all these relations pop up over and over again, even though you start from different models and define quantities, stochastic thermodynamic quantities for different kinds of models, you very often find these same relations. The other one is the fluctuation theorem, which you get for setting p of x, p1 of x equal to p of x tau, which is the solution of the Fokker-Planck equation. For initial distribution P0 of x. So we take, of x0. We take this, an arbitrary initial distribution, which in principle an experimentalist can prepare, and let it evolve according to the usual dynamics. And the end distribution here is what we get from the evolution of the system. And when we plug this into this equation, we get a contribution from the system entropy. Okay, I leave that to you as a homework, but the result is from this relation here that the change in total entropy averaged is equal to 1. So this here is then the integral fluctuation theorem for entropy progression. And now I'm done with what I wanted to show you, and I apologize that it took even longer than expected, but still, do you have any questions? I mean, we have the whole afternoon to discuss, so I understand if you want to go for lunch now. And sorry? Yeah. We can start the presentation a bit later. Okay. can we start a little bit later with the poster presentation? I'm sorry, I was all the time in the